Okay, so what we're going to do now is develop a tool that we can use to graph, using a different technique, pretty much how the most textbooks will teach these graphing. I just don't like it because you can't really build off of it to do anything else that you'll do in the future. But if you're more comfortable with it, I might as well give some lessons on it. So the other technique that you'll use, instead of using those inequalities, in fact, most textbooks will use the graph to give you the inequalities. So what they use instead is a little bit of analysis, as well as investigating end behaviors. So pretty much I'll just do everything in reverse from how I taught in the other video lesson to do these graphs. So the first property that they'll use is that we can figure out end behaviors of a polynomial by just looking at the leading coefficient and the leading term. So we'll go through an example to explain how it works, and then we'll just do it a little bit more efficiently after the first example. So we don't really need all the background logic to be able to put it together. So we're going to look at what happens as x gets sort of very, very large. This is what we would call the end behavior. So either your left or your rightmost ends of the graph, right? As x goes to infinity, that means that the graph, it's basically, so you have your picture, it's telling you what's going on as x goes to infinity, that's far on the right, and what's going on the left, that's x going to negative infinity. So it's telling you what's going on the outside ends of the picture, essentially. And so we want to know specifically for this third degree polynomial. So for this one example, I'll go through it in pretty thorough detail. What we can do is we can actually sort of factor out a large chunk from the p of x. There's no common factor in all the terms, so what we're going to do is force factor the x cubed, the largest power of x. Sort of like with the transformations, how we needed to force out the coefficient of the x to get the nice order. We're going to do the same thing here. It doesn't factor nicely, so we're going to force it to factor. And so what I'll have here is p of x equals x cubed, and I'm going to force it out. So the first term is going to be 3, and when we factor, we divide all the terms by that x cubed. So 5x squared is going to be 5x squared over x cubed. It's going to leave me with an x on the bottom. And then x over x cubed is going to leave me with 2 powers of x on the bottom. And then divide 1 by x cubed. So we force it out, and it looks like this sort of ugly thing here. So the idea behind why we would possibly want to do that is because it's actually really easy to investigate what's going to happen to these chunks here. So if x goes to infinity, what we can think of that is x is very large. You can just think of it as a very large number, like 1,000, 1,000,000, 1,000,000,000. So 5 over x is 5 over a large number. And so if we divide 5 into 1,000,000 pieces, those pieces are very small. And so if that's very, very small, what we can do is say that it's basically close to 0. So we're going to get the same logic for each of these things. This thing's close to 0. This will also be like 2 divided by 1,000,000 squared is basically 0. 1 divided by 1,000,000 cubed is basically 0. So what I'm going to get is that p of x, it's not equal to, but it's in theory close to x cubed times 3, or just 3x cubed. And so what you can see is that this is actually just the lead term and coefficient, the leading term of my polynomial. And that's really all that's going to matter for dictating this sort of end behavior. So now what I look at is if I do P of a large positive, so that's basically infinity, right? A large positive, I would get 3 times, not quite, but it's basically 3 times a large positive cubed. So if I cube a positive, what I'm going to get is a positive. And if I cube a large positive, I'm going to get a much larger positive. So as a result, what I will get is a very large positive, which would be basically infinity. And if I do the same thing, but with a large negative, it's my P of negative infinity. That's terrible notation. Don't ever write P of negative infinity. So I'll put quotations around that. That's basically looking at P of a large negative. And so this would be basically 3 times a large negative cubed. And if I cube a negative, I still have a negative. And so this would be negative infinity. And so that's going to actually tell me these behaviors. So as x goes to infinity, maybe we'll do the first one in green. X goes to infinity, that's right there, that large positive. And so what happens is it goes to infinity. And so graphically, how I can describe that is it means the graph goes to the right and up. And for the other one, let's do that in red. No, let's use pink. So x is going to negative infinity. That's kind of like plugging in a large negative. Oh, I did use pink already. Clean it up. Let's try burgundy. So I'm plugging in my large negative, and we saw that the output was that negative infinity. So as that happens, the answer to this question would be that P of x goes to negative infinity. And so as x moves left, y moves down. So we'd be getting something like this. And so we could actually put that together to get an idea of what's going on in the whole graph. We haven't investigated the middle at all, but I know that on the right, it goes up, and on the left, it goes down. So that's how we can determine what's going on the outsides. And then we use the zeros and some stuff we've talked about before to figure out what's going on the insides. So we'll do another example a little more cleanly. How we should be able to do these 2 examples here. So we're going to look at the end behaviors of this simplified polynomial, 4th degree polynomial first, and then we have a factored q of x over on the right. So to deal with the first one, as mentioned before, it's always just that leading term that we really only care about. So that 4x to the 4, because we can just sort of presume that these, the 3x squared and the 5 are not small, but small in comparison. So like if I plugged in a really large number for x, the first term would be very large. The second term would also be very large. And 5 would just be 5, which is small. But if I do a large minus a large plus a small, we don't really know how, like just by looking at it like this, I don't know how the larges interact with each other. But the degree 4 tells me that that large number is way bigger than the square. So it's going to dictate the total behavior. And so really all I need to do is sort of think about what happens when I plug in infinity to x to the 4. And even though I'm not being filmed, I just made air quotes about plugging in infinity, but that's what we're gonna do. I'm gonna always put quotes around it because it's terrible notation. Yeah, so we'll look at x going to infinity. So what we'll just do is look at 4 of, again, I'm gonna put quotes around it because it doesn't really make sense, but that is a positive infinity there. So it's 4 times a positive to the 4. So 4 times a positive large number is still just a very large number. So my p of x will go to positive infinity. So that's the first answer. And if x is going to negative infinity, again, we'll just look at that first leading term. 4 times a negative large number to the 4. Now that negative is going to get sort of squared away because of the even power. So that'll become a positive, and that will also go to positive infinity. And so we can say p of x also goes to infinity. And so what that tells us is that on both sides of the graph, if we were to try to draw this, we don't know what goes on in the middle, but on both the left and right, it's going upwards. And then we use other tools to figure out the middle. Okay, for B, this one's all factored, but we can figure out the leading term of this by just multiplying all of the leading terms, including their multiplicities. So the leading term will be x times 2x cubed. And so what we would end up with here is 8x to the 5. All right, so just by taking an x, because there's only one x there, there's only one x in the x minus 2, and then the 2x minus 1 gets cubed. So we need all those multiplicities, and we clean it up to get that 8x to the 5. And so we just look at the same analysis. If x is going to infinity, then what we've got is 8 infinity to the 5. And that should clean up. It's all positive, so it's going to stay infinity. So then q will go to, I'm just being lazy and not writing q of x, but it doesn't matter too much. Q will go to infinity. And if x goes to negative infinity, then this 8, if I do now a negative large number to the power of 5, the odd power is going to keep it negative. So it's actually going to stay sort of negative infinity. And this will look kind of similar to the previous graph in that one side goes up and one side goes down. In fact, if your degree of your polynomial is even, both sides should do the same thing as we have on the left there. They might both go up or they might both go down. And if the degree is odd, they'll go in different directions. This one should look like this. And so that's your sort of your end behavior analysis. This is touching a lot on something you'll learn at the start of calculus called limits. That's technically what we're doing. We're pushing x towards something, and that something is infinity. And we're investigating what p does as x moves towards something. So this is essentially we are evaluating infinite limits right now without using the word limit. And again, that's another reason why I don't really like teaching this method to do graphs, because you're doing an analysis that you really don't have a lot of background to do. And if it doesn't sink in right now, I mean, it shouldn't, because you don't know what a limit is right now. Well, this is kind of a limit. So there's your intro to calculus. Yeah, so the last lesson, we'll just kind of wrap up how we use this to graph, because obviously I've got little bits of graph here, and what we need to do is fill in those question marks.